to this presentation. My name is Chad Breslin, and I'm going to talk to you about how to design your ROV for performance, as well as give you some questions and sources to help you think of some design ideas. First of all, there are some constraints that we must follow. MATE does limit their amperage allowed to either 25 or 15 amps, has a fixed voltage of 12 volts, and of course, there is a time limit. With this time limit, there is a need for speed, so just remember that with a smaller and lesser weighted ROV, you can go faster and vice versa. In addition, if there is more topside mass rather than on the bottom, we can go even faster. Next up, we want to minimize our losses. Fluid drag is a force that can slow down the ROV, which is something we definitely don't want. We also don't want to be wasting electricity caused by wire resistance and poor connections. We should also consider that maneuverability depends on the vertical distance between the center of buoyancy and the center of mass. In the real world, ROVs go down once and up once, so keep that in mind to maximize time. A design philosophy is very helpful to sort out ideas. For example, a former teen used the philosophy of simple, sexy, and reliable. Simple means to not overcomplicate it, sexy means to make it look good, and reliable means that it should be neat and parts are easily swapped out. Some frame design questions to consider are what materials you should use. Is it going to be an open PVC, closed PVC, acrylics, or some combination of that so you can keep your weight as low as possible? How is the ROV going to be shaped so that drag is minimized? What is the weight and buoyancy distribution going to be like? And what are some other constraints in the tools and skills available? Some propulsion questions to consider are how many motors is there going to be and what orientation should be in the frame so that we can go forwards, backwards, fast left, fast right, slow right, up, down, and strafing. What are the right size propellers and shrouds for the motors? How much power does each motor need? What orientation gives maximum speed? And again, what constraints are there going to be, such as cost, weight, and size? Going deeper into the motors, you can improve the performance with different sizes. One of your jobs is to do the worksheet that you will have to select the best motor available. Some questions for control designs are how many pilots will there be and the human interface for each pilot. What motors there needs to be on and off for you to go in the direction you want to be. What are the motor conditions that cannot coexist? And then what needs to be waterproofed and how will you test it? Are there any limits to your control system? Will the ROV be able to continue working despite a malfunction? Will you use a joystick controls or Arduino controls? And again, what are the constraints? Typically, your ROV will need a camera to see what's going on, so some questions to consider are how many cameras will be used and will they be waterproofed? Where are these cameras going to go? How many displays will there be, and how will the equipment be protected from power spikes? How do you keep the video signals clean, and how are you going to mount the video so that it can be adjusted? And finally, what are you going to do if a camera fails? The ROV is connected to the controls by a tether, so we need to consider how long do the tether need to be? What signals will it carry, and how many wires are needed? How are the power, video, and control signals separated? What gauge are the power wires, and how do you know that it is optimal? How is all of this equipment going to be protected, especially from the water? The last set of questions are power and ballast design. How many fuses are needed to protect the equipment? How do you know that you are approaching too much power usage? What are you going to do if a motor gets stuck in pool garbage? What is the water pressure going to be at the operating depth? What ballast material will be used? And what water pressure can it take? And finally, how do you figure out how much ballast is needed? The sources of all of this material are the Underwater Robotics textbook, as well as MATE technical reports found on the interweb from previous regional and international winners. Your homework will be to complete the worksheet. Thank you for your time and good luck.